how do you teach a machine something that is too difficult to define explicitly? How can we get the machine to learn from reinforcement? From, hey, that's bad, don't do that. Hey, that's good, do more of that. It's kind of how the brain sort of works, right? Well, this is a field in AI called reinforcement learning, and I sit down with Dr. Giacomo Spigler to speak more about it. He is a professor in the Department of Cognitive Science and AI. He teaches the calculus course. That's where I first met him, but he also does a lot of work in reinforcement learning and robotics. And yeah, it's an awesome conversation. I hope you learned something. And yeah, please enjoy.
Yeah.
Yep, we're live. What's up, man?
Yeah, all good. Just tired. This semester is actually really, really busy. Probably the busiest I had at Tilburg University so far.
Like
in a good way, but
because of like the work with the thesis stuff, or like what's the
yeah, a bit everything. So we have of course the second semester is busier because we have more classes to teach.
You just bring it a bit closer to your face.
Yeah. So it's busy because there are more classes, but also we have so many projects starting. We have the new robotics lab, the AIR lab, or AI for robotics, that is also starting this semester. Well, at the end of this semester.
You want to say something about that real quick?
Yeah, so it's going to be me and Murat, we manage the lab, and the lab is going to be the first actual robotics lab at Tilburg University. So we are planning a lot of projects already. We're going to get a PhD student with the NWS starting grant from the government. And it just takes time to set it up because we still don't have an actual room, but we're going to have it in a couple of months. So there are going to be a lot of exciting demos and a lot of exciting research being done there.
It's going to be on campus or in like Mind Labs?
It's going to be in Mind Labs.
Nice. All right. So, well, I sort of primed you for what I wanted to talk to you about. But generally, let's focus on some reinforcement learning stuff. Okay. So the boys and I, we started like journal club. And every month we sit down and talk about some paper that we want to discuss. And the last one we did was Andres. He suggested that we do the deep reinforcement learning, human level control through deep reinforcement learning that was released by was it OpenAI? No.
No, I think
DeepMind, right? Okay. Where do you want to start, man? You can take this where you want to go. Like, how do you want to, like, if you were going to talk to a random person about this, how would you start?
Yeah, I don't know if you have a question, because I have reinforcement learning is a massive field. So first, for the viewers, a definition can be that reinforcement learning is a branch of machine learning that deals with learning behavior. So that's important because if you want to learn a behavior like a self-driving car, you could do it theoretically with supervised learning. You just collect a lot of data, you steer the car, you collect what is the action that the human did when driving a car, depending on the cameras, what the car is seeing. And then you can train a supervised learning model on that data. It turns out that this does not work because there is so much more variety in the experience that can be collected. So we never, if you're driving a car, there will never ever be two identical frames from a camera when driving a car. So neural networks do generalize well, but in this case, they really risk overfitting and then picking the wrong action. So if you get up on a new road that was never seen before, and you train the network with supervised learning, it is very likely that the car will just pick some random actions and then you go off-road. So if you want to learn behavior, there is a better technique, that is reinforcement learning. Reinforcement learning works in a way that is somehow similar to how animals learn. And it is by learning by reinforcement. What we mean by that is that when by evolution, our brain is designed to learn new tasks fast. And learning is done through some reward signal. A reward signal can be if an animal finds food in the wild, then it's happy. Or if you get a predator, it's really scared, and then need to remember not to go near, a lion's nest, anymore.
Lion's nest? I don't think.
Yeah, I don't know. It's just like like a den, like the area where there are the cubs. So the idea is that an agent can do different actions and then observe whether the action has a positive or negative outcome, and then use that to understand or try to understand which of the many actions the agent did so far contributed to the positive negative outcome that was observed. And reinforcement learning deals with finding a way to assign this score, positive or negative, to the specific action we're done, to understand which action contributed to the good or bad outcome, and then either try to repeat the good action or try to avoid the bad action. And it turns out that this very general approach, there is an hypothesis that is very widely shared in the field, not by everybody, but I would say by the majority, and that there is a paper from DeepMind about it, and it's called the reward hypothesis. And that hypothesis says that any behavior we might care about, in our world, or that a robot could do, a car can do, a computer can do, can be expressed as a reward function, so that there exists a reward function such that if you train an agent using that reward function, that is when to give and how much reward to give or punishment to give, then the agent will learn to solve the task we care about. And if that is true, which I think it is probably true, then it means that we can engineer reward functions, and then we can have agents learn anything we care about.
Okay. So this is one thing that came to mind when you mentioned figuring out what to learn. So basically, the question is, how do we teach the agent what to learn, right? And the space of, let's say, for example, driving a car is like so vast, and that's how so Tesla is a purely reinforcement learning stuff.
No, I don't think they use reinforcement learning at all. I think they use it in some parts, but I think it's mostly deep learning for vision to detect obstacle and the likes. And then I think they have a kind of handcrafted policies to control the car.
Oh wow, I didn't know that.
I think that they definitely try different approaches, and it's also secretive. But all the self-driving car companies, I think that they probably do some models for driving. In practice, it's not that difficult. The problem is that there is so much variability in the conditions you can encounter. But if you can steer a car and keep it within lane, you have a GPS, and you know which roads to take. So you have to recognize which road is which. But it's something that you can kind of engineer by hand if you had a reliable perception system.
So if you're doing in terms of people doing reinforcement learning, it's a lot of companies. So how do we go from academia reinforcement learning stuff? Is there some application right now being using reinforcement learning?
Well, one very famous one is ChatGPT. ChatGPT is actually fine-tuned using reinforcement learning. So that is definitely starting to get used more and more. For many applications, some companies are trying to do it, but it's still not mature enough as a field. So I don't think there are many actual applications that use it. But again, this became more popular.
So Dota 2, the OpenAI's Dota thing, was that?
Yeah, but that's not used in practice, right? It's only for research and for special competitions. But also AlphaGo to win, that won against the world champion at Go. There definitely are a lot of state-of-the-art superhuman performance agents, but for actual day-to-day application, it's still limited. But it will get there. There are only some problems, so that will be fixed. One is that it is much more compute intensive than standard deep learning, so you need more powerful supercomputer. Then the field is not mature enough yet, so we did not get a Keras or TensorFlow moment yet with reinforcement learning. The software infrastructure is fragmented in a lot of different libraries. They are kind of converging to some kind of unified standard, but they are still kind of different. So that makes it more difficult to get started in the field. Then the field per se has more complexity than normal machine learning. In normal machine learning, you have a data set, and you can, if you change the model, you still use the same data set with the same interface. But in reinforcement learning, an agent has to interact with an environment. So you have to make code because you don't have a data set. The data set is collected through the interaction between your computer and the environment. So you need to write code that supports that interaction.
So even a lot of the, if I understand what I've read, very little bit, but even the fancy Boston Dynamics stuff, that's more like
that's absolutely in zero reinforcement learning.
Yeah, control theory.
Yeah. That's a typical robotics company with typical robotics method. They develop at a very impressive level of performance, but it's still kind of old school robotics that I personally don't think will have a place in the future. because it is all fancy and nice. But the demos you see of Boston Dynamics are only the good ones. There are videos from Boston Dynamics in which you actually see a realistic experiment, and you see that 90% of the time the robot that tries to do all this fancy movement around the obstacle course just misses a step and fall. And of course you don't see those in the good videos. So the thing is, with this is more connected not only to reinforcement learning but in general to what is called end-to-end robot learning. This I first heard about it from colleagues at DeepMind, I think in 2019, 2020, so it was a bit ago. So this is not something new that I'm coming up with, but it's well known, but still not that developed. So first, what do you mean by end-to-end robot learning? We need to think of how robotics work nowadays. In traditional robotics, you create a system by handcrafting the system, kind of like a machine learning versus deep learning. And when you handcraft the system, you might want, for example, to detect a person, like a face, and to detect the face expression from when the person is smiling. And that means that you have to you usually make a module that uses computer vision or deep learning nowadays to detect faces. Then you crop the face out of the image and you run another neural network to detect the face expression. Now imagine if you change the light intensity in the in the room. If one of these two modules, like the face recognition module, does not detect the face anymore because the light condition changed, then your whole robot will stop working because it does not detect any face, even if you're literally in front of the robot. So that's not very good, and it can break in very very easily. If you make a robot that does a very complex behavior, you start getting many of these modules, and the more of these modules you have, the more it is likely that the system will break down, because if a single module breaks, then the whole system breaks because it is lacking crucial information. Now, in end-to-end learning, instead, we use a single neural network, a single model in general neural network, that goes from raw sensor data, for example, cameras or motor sensors, and produces motor actions as output. So we know human in the loop, but they can be human in the loop, but not human designing the system with the module. The idea is that, like with deep learning versus machine learning, if this network is learning to do a task and that requires detecting whether a person is smiling, it could learn to detect some features that are much more reliable across, for example, lighting conditions without needing to detect a face. So the system might, for example, detect that there is a person smiling without detecting a face in the image. But that could be enough for doing the task correctly, and it could be more reliable because there will not be a single breaking point, but it will be like a full monolithic system.
So the idea is to let the system learn the representation that it needs. Yeah,
exactly. Because when we create our own representation, like with machine learning, we introduce our own assumptions, but our own human assumptions are usually wrong in this case, because we think that in order to do the task, you have to detect that there's a face and that there is a smiling face. But maybe it turns out that the robot does not need to know all that information, or does not need to know the XYZ coordinates in centimeters, of the face with respect to the camera to do the task. So sometimes, when you do robot grasping, you need to detect an object on a table, and you have to know the precise coordinates in millimeters of where the object is with respect to the robot, so that then you can control your robot arm to reach the object and grasp it. But we humans don't know the coordinate with that level of precision. We know roughly where the object is. Then we start moving our hand towards it. And when the hand is closer, we kind of do visual serving. So we know what is the relative distance of the hand and the object. We know which one is a bit closer because stereoscopic vision. We know whether the object is a bit to the left, a bit to the right. And then we adjust our movement. We don't need the precise location.
Speaking of adjusting movements, one of the things that blew my mind is so when you're walking in the rain, when you're walking with an umbrella, our ability to just to adjust the umbrella to the wind, that's nuts. That's insane. I was walking around and I was like, what the hell? I was reading and then I was like, man, the fact that I can do this is insane. Right?
Yeah.
Because I don't think about the differential equations you need to model that, right? It's
So if you were to do it with a robot in traditional robotics, you would actually have to do all this engineering, of the physics and the control and everything by hand. With end-to-end learning, you just let the system learn only the thing it needs. Okay. The downside is that it could overfit to only certain conditions. So you, as usually with the machine learning, you need to have a very wide variety range of conditions to be able to make the model learn.
So how do you generate those wide variety of conditions?
Yeah, so in robotics, with reinforcement learning and end-to-end learning robotics, we usually use simulators because this process may sometimes require a lot of data and a lot of time to learn in terms of interaction between the robot and the world, not in training time, because you can use a supercomputer and that can be arbitrarily fast. But in terms of data collected of the interaction between the robot and environment, it needs a lot of data. So in order to do that, the only way to do is simulators. At the beginning of the field, I think 2017, 2016, Google tried to build a robot farm with I think 20, 50 something robot arms. Actually, pretty expensive one. They spent like a few $1 million on that project. So they basically put these robots one next to each other, and they made them do the same task in parallel. And the idea is that if you have 50 robots doing the same task in parallel, you take 1/50 of the time of interaction with the environment to collect the same amount of data. And it still takes a long time, but to learn, you can learn some simple task within 1 or 2 hours of interaction with the environment, multiplied now by these robots. But that is unlikely to scale because that's a very simple setup. Some tasks, they are not easily reset like that. Some tasks cannot be done like that. In some cases, you might have robots that are much more expensive, so it's not always possible. I mean, and even if you can do it, it's still really, really insanely expensive.
We've had the benefit of billions of years of evolution, right?
Indeed, so we don't have to learn everything from scratch.
Yeah, so if you're trying to reinforcement learning and teach a robot how to play Go.
But I don't think it's a major problem because it just requires a change in attitude. What I mean is we are witnessing an era of large models, like a large language model, for example, but not only them. And they are called in the field foundation models. So they work as follows. These models are actually not even trained for meta learning, to learn faster new task. They actually do zero-shot adaptation. So without new data, they can adapt to new task. And that's because they are a very big model. They have a lot of acquired knowledge. And it turns out that with GPT, if you use a different prompt, you can actually specify different task. And that it does not require retraining. But ideally, you might think that the model could be trained to be fast, rapidly adaptable, for example, using meta learning, and then you can just do fine tuning. So the idea is that if you have this big model, you don't need to train it on your own desktop. You can train it to supercomputer, even spend like $1 million by a big company to do it. But once you have it, you have to train it only once. You don't have to train it again. If you want to adapt it to your own task, you add your data and you fine-tune it, and that you can do on your desktop because that is much faster and requires much less data. So in that case, what the supercomputer is doing with these few million euros is what evolution did for us, in a kind of light parallel. And then when you're fine-tuning the model, you're just doing like some simpler learning. So that is not a big problem. It is a big problem because you still need these big resources to do it, but there are a lot of players doing it, and universities have access to supercomputers. So we can also, not at the scale of OpenAI, but we can definitely do experiments in that direction.
So I feel like reinforcement learning for robotics is like a magnitude level difficulty in terms of
but it will become easier. So it's just that it requires a lot of software infrastructure to set up kind of a sort of make it simpler for people to use. And also the other thing that robots are expensive and every robot is different, so you have to customize your code for every robot. So we need a bit more standards in the field. But the more people start working on these topics, especially if they open source the code or they write software libraries to make it easier for other people to use it, the more it will become easier to try out these things on actual robots. And then the more people will be able to enter the field, and then you get even more productivity. It just takes a while, but we're trying to make it faster. So
we've been trying. I mean, reinforcement learning has been evolving for a while now, right? Like the field has been doing some stuff. Like I remember like some really old attempts to get hands to do certain things, but it required so many training iterations and repeating and like getting thing. But the OpenAI has their own hand, right? They can do the whole.
Yeah, that's like a $300,000 by Shadow Robotics.
That's crazy.
Yeah. But now, for example, I think they changed that. Was I think in 2018 or 2019 with the OpenAI demo with the hand, and that required 10 to 40,000 computer cores to train plus 60 GPUs or something. Nowadays, you can reproduce part of that experiment on your own desktop because NVIDIA has released a physics simulator that runs fully on GPU. So you train both the simulator and your agent, everything runs on the GPU. And then you can get a massive throughput of data collection. So in a couple of hours on a decent GPU, you can get as much data that was collected by OpenAI with those tens of thousands of computer cores. So nowadays you can do it. It's actually a bit more cheaty. There are some differences so that the experiment you're running on your computer is not really compatible with the one by OpenAI. But if you have to do that, you still get a pretty decent throughput. So you can still get some of the benefit. And that means that it becomes easier for people to do this research. But it's still difficult to use this software though.
The future of robotics, you would say, is reinforcement learning? Is that the just?
Well, in general, end-to-end robot learning. So reinforcement learning is one thing. Reinforcement learning has some problems aside from the compute time. A problem is that it is difficult to specify a reward function for a task because you have a task in mind, like turning on, like making coffee. And you can specify it with rewards. You can say, okay, I give a reward of 1 if you actually make a coffee and 0 if you don't. Okay, it will take forever before the robot by accident makes coffee and then get a reward. So it will never observe any reward. So that's not a good reward. It's intuitive, it specifies the task, but it's not good for learning. That's what we call a sparse reward. Because for most interaction, the robot gets no reward, so it does not know if it's doing well or bad. Now, then you can make it more dense. Let's say you make individual steps, like turning the coffee machine on is the first step you definitely need to do, or grabbing a cup. And for all of this, you just give a reward of 1. Okay, the robot learns to turn on the coffee machine, then turns it off, then on again, off, on. Very simple, not making coffee, collecting infinite reward. So these agents can learn to cheat very easily. And usually they will learn something that is not what you meant. So after training this agent, you see that it does not work. You see what didn't go wrong, and you try to modify the reward function to solve the task more effectively. And it can take a lot of time. And if one of these training settings takes 1 or 2 days to train and to test, and that's still very fast for reinforcement learning standards, it will still take a long time to do the fine-tuning. So instead of that, we have different techniques. One that is very powerful and becoming popular, but still not mature enough to work in practical context, is imitation learning. So imitation learning collects observation from humans. So for example, if we have a robot arm making coffee, you could put the robot in impedance control and then literally grasp the robot arm and move it around to make it do the action to make coffee. And after doing a few repetitions, you collect this dataset and use this to introduce some prior in the robot. So you kind of pre-train the robot to mimic those kind of trajectories that were shown by the user.
I think some industrial robots do that, right?
That yes, but that's without reinforcement learning. They're just memorizing the trajectory.
Yeah.
In reinforcement learning, you might want to have a robot with a camera looking at what it's doing, so that if you move the coffee mug, you want the arm to move to the new correct location, right? Not to the same location as before. But so you want to show a lot of example, and you want the robot to generalize so it can learn what was intended. Another thing is it can just be observing human or doing this kind of data and trying to infer what is the reward function that the human is using in that setup. So if the robot observes a human making coffee, or a human moves the robot to make coffee, then the robot can can collect these rewards and then try to make a reward function that, if used for training, would reproduce that type of trajectory of movement. And then you can use that for training. One last example is that is also becoming popular now, and that's actually what was done with the ChatGPT, but it's not the first time it was used. It's reinforcement learning from human feedback. That means that we humans can look at the robot, so there is no reward function, and the robot is just learning. So let's say that you take a reward function parameterized by neural network. At the beginning, it is random weights. So you give like an image as input, and the reward function neural network will just predict a random number, right? Or 0, so nothing useful. And the robot starts learning with that reward function. Now, the reward function is meaningless, so the robot will just do random movement. That's fine. Then you get some human participants, like on Mechanical Turk, that watch some short videos of a couple of seconds of robots doing, in simulation, doing different behavior. So you just collect these snapshots of videos of the robot moving at random at different times during training. Then you give them to a person, and the person has to say which one of a pair of videos looks a bit closer to achieving the solution. So the robot is moving at random, but maybe in one video is moving at random closer to the coffee machine. So you think, yeah, that's a bit better because it is more likely to get to the objective than the other one. And then you collect a dataset of these preferences from the user, so which of the two options is better. And then you use them to train the reward function model So that basically you run this neural network twice on the 2 videos. And each neural network will predict, they're the same weight, so the same neural network, but they predict a different
Bring this thing
score.
close to your face a little bit.
Yes. There
you go.
So this the neural network will be run twice on 2 videos, and we output a certain score, like how good that behavior was, and then the neural network is trained to match the prediction of the user. So you want the highest score to be assigned to the video that was slightly better behavior. After doing that, you get a slightly better reward function that is keep getting used to modify the robot behavior, and the robot learns to do something that matches a bit more the human preference. Then the more you get close to the task, the human keep updating its preferences, so the reward function keep getting updated to basically learn what the human prefer. So if the neural network needs to replace the human, so if the human looks at these 2 videos, say which one of the 2 behaviors is better, we want the neural network to be able to do it by itself, because then we can just run it supercomputer and do training. And turns out that the more you do it, after a while, this reward function learns the human preference very well and can predict which behavior a human would prefer. And then you use that to train the agent. And after using that, the agent does the task. So this is also very powerful. And again, it's what was done with ChatGPT. In ChatGPT, actions by the agent were defined as sentences generated by ChatGPT or by GPT, and then users were shown different generated text from the same prompt. So I think they were given the prompt and like 2 alternatives of generated text. And users had to rank them. So let's say which one of these 2 generated text looks more natural, looks better, looks more appropriate for this prompt. And then they trained this reward function neural network that was taking these 2 sentences and were trying to reproduce the preference of the user.
So what about code? You did the same thing for code?
There is a GitHub Codex, which is a version of GPT trained on code.
Yeah.
And the difference that it does not only generate code, but there is a layer on top of that that double checks. So it can generate a couple of different alternatives for the code and then ranks them. And then there is some hand-designed code that checks syntax to make sure that the code generated is actually safe and correct and will run, at least syntactically. So if you use a ChatGPT to generate code, that's very bad because it does not have this check. So it can generate the wrong code. But if you use OpenAI or Microsoft Codex, it was a GitHub Copilot and OpenAI Codex. So it's like the technology and then the actual product. And if you use that, you get integrated into a Python editor, and it just generates code that is again more syntactically correct. And that is trained only on code, while ChatGPT is trained on any language. So that is not designed for writing code. So there are better tools to do it. And
so one of the problems. How do you? So when you take this is a problem that we have as human beings. It's like when you do a certain sequence of actions and we get a reward, figuring out which of those actions actually contributed to getting the reward is a problem.
Yeah.
How do you try to address that in?
Well, there is that's called a credit assignment problem, and it's a big problem in reinforcement learning. But there is the idea is basically to use statistical regularities in the data. An example. Imagine you have a game of Pong, so you can move your paddle up and down, basically. So these are the 2. Let's assume that these are the only 2 movements you can do. In practice, you can just not do any action or a couple other things. But let's say that you only move up or down. So an episode consists, you get a trajectory of movement up, down, up, down, whatever, like just a sequence of this kind of action until you get to the end of the episode when either you score a goal and you get a +1 reward, or the opponent scores a goal to you and then you get a -1 reward. So what you can get, if you repeat this many, many times, you get a lot of sequences, basic kind of strings, up, down, down, up, blah, blah. And then at some point you get which one is 1, which one is -1. What you can do, for example, this is actually conditioned on the pixel, so you actually see the screen. And you can see that if you do it many times, maybe you see that there are some similarity. Like if you have the ball moving toward very close to you and moving up, every time in these long trajectories in which you moved up, you actually, in the end, got a +1 reward. And every time that was the case, so the ball was moving up towards you and you moved down, the episode terminated with -1. So you can associate that in that state, selecting the action up on average, resulted in a positive reward, while selecting the action down resulted in a negative reward. So you know that action, that state, was the action that was contributed. But if you do this average over many episodes, you will see that many actions up and down don't have any value, because if the ball is far away from the paddle and you move up or down, it doesn't matter, as long as they haven't gone too far. And if you average this over many trajectories, you will see that those have no value, because if the ball is far away, you press up. 50% of the time, you get +1, 50% you get -1 in the end of the episode. When you press down, you also get 50-50. And then you see that action did not really contribite, right?
Okay, so you depend on the statistical regularity.
Yeah, so you just have to collect a lot of data and see, on average, when I select an action similar to this action, in a state similar to this state, did I get more positive reward or more negative reward, for example? And if you collect many examples, and you can generalize, make a good representation that it does not have to be exactly the same state, but something similar, you can detect some regularity. But for example, if the ball is very far from the paddle, then it doesn't matter. Sometimes you get plus rewards, today you get minus reward, but it will be independent from the action you get. So the proportion of positive and negative reward you get is the same whether you moved up or down. And that means that action, in the state, the action they choose is irrelevant. But in some cases, you will see that in those crucial points in which you're about to get the goal scored against you, if you press up or down, you actually change the outcome. And then you see that in that state, by pressing up or down in the direction of the ball, results in many more positive reward than negative, versus if you do the opposite action, you get many more negative rewards than positive, and then you know which action to do and which one to avoid.
Yeah, so over given enough examples, you can build a distribution of what to do and sort of extract.
So it is that you can get this credit assignment by just looking at what happens. So if you select, imagine you get like another example that we do for analyzing this model theoretically. It's called the multi-armed bandit, and that's a terminology from Las Vegas. There's like the slot machines, and they are the bandits because they steal from you, all your money, and they are multi-armed because you have many slot machine, and different machine can have different payouts. Now, it is never deterministic. So, for example, the reward can be normally distributed. So they have an average reward, and then there's be a standard deviation. And you don't know what is the average reward and the standard deviation. Now, actual slot machines are more complex, but this is a simple model. Now, if you want to make money, you would definitely want to get the one with the highest expected payout. Like, you can just compare them. But you don't know which one it is, so you have to make experiment. So you play on the first one, and you observe a certain number, like 5 reward. Right again, you get 15. Another one, -5, And then the more that you collect, the more you can build a distribution that matches that, and you can actually infer the parameter. But you don't want to waste too much money on that just to explore, because if you see that you never get more than 10, another machine always get more than 50, you just continue in the other one, right? So you have to be able to make these inference. So in that case, the regularity is...
you need to balance like the cost of experimenting to learn the distribution and the actual benefit of learning the distribution, right?
Yeah. In that case, yes. So in the real world, it can be a bit more complicated, but in this case, that's all they have to do. So if you do a sequence of slot machine, like 1, 2, 3, 4, 5, 6, and you just try all of them once, then you see some reward. If you get a high reward on one, it is not necessarily the best machine, because maybe it is just on the tail of a Gaussian distribution, right? So you need to do more interaction to be more certain. So it takes more time. But after you observe them, if you keep playing them at random, you will see that some machine on average will give you more reward than the other. Just take the arithmetic average, for example, and you see that some machines are more consistent, and on average they give you better reward than the others, right? And that's the same as detecting the regularity of going up or down with the reward, because playing that machine correlates with a higher reward than the others. In the case, there's only one action and an immediate reward, so it's a bit easier to do the connection. But just play a sequence of a slot machine, you see that in the sequence, in those sequences in which the best playing machine is played, you probably get a higher reward. In those sequences in which you don't play that machine, you get lower reward. And after a while, you learn now that the only thing in common with those sequences of which machine you played is that one machine that was the best playing. And then you learn that is the one you should play. So it is not very intuitive, but reinforcement learning algorithms basically manage to extract this information.
So it all depends on how many times you can play that thing, right?
Also, yes. So that's called the exploitation dilemma. So you have a behavior like you actually paying real money, and you have to find which machine is better. Ideally, you would like to play all of them infinite times so that you get the best representation of the distribution.
We can't do, like, human beings can't do that.
No. But also you would pay like infinite money, right?
Yeah, exactly.
So you cannot. So the idea is that you would like to make as few attempts as possible, so that you don't waste money on machines that have lower payout, and then you want to play most of your money on the machine with the highest payout. But again, you don't know which one, and it cannot be certain ever, because it could always be on a tail on the distribution. But the more you play, the more you get certain. So there are algorithms in which you can actually prove mathematically what is the optimal strategy. And it is that it also depends on the variance of the machine. So you can try different machines and basically rescale them. When you do an estimate of the average, usually do Monte Carlo. So when you use the arithmetic average to approximate the mean. And the quality of the estimate, like the variance of your estimate of the mean, improves as 1 over the square root of the number of samples. So if you want to put your error, to make your error 10 times smaller around the mean, you need to collect 100 times more data. But this puts fun. And then you can say that if the payout is small and you have enough samples, stop, because you don't need to test it anymore, because it will not change too much. But if the payout has a high variance, you might need to test it more. So there are basically some rules in which you can actually create a reward function that assigns both the reward you observe from the machine, and then you also rescale it by 1 over square root of the number of times you played that machine already. In this case, if you underplay a machine, you're only playing the best machine, the reward this machine gives you kind of keep going down. At some point, you are forced to try another machine, because this actual payout, this kind of fake payout you get, is going to be higher. But if you keep playing the new machine and the reward is actually still small, then the best machine becomes the best again. So you keep playing all of them, but you spend much more time on the best one. But this guarantees that asymptotically you get the best performance. So you pay the less money and you get the maximum payout.
So how much of how much of things that you learn from inspiration we get from how humans or animals learn?
Well, let's say in reinforcement learning, it's kind of an example of convergence in science, because there definitely was a clear biological inspiration, but when reinforcement learning was first created in computer science, there was not yet a theory of reinforcement learning in animals.
What's the simplest reinforcement learning model you could build? If you just like write some code in Python, build something.
I think now that we have a very well developed and very powerful PyTorch, I think of decent performing algorithm, not simple, because there are maximum entropy. If you want to like a cross entropy reinforcement learning, there's some simple methods that are easy to implement, but the actual deep reinforcement learning one, the easiest you can implement policy gradient, because that is kind of you want to maximize the rewards you collect from an environment. This is a non-differentiable function, but you can actually use a trick, and you can actually write as a function of the behavior of the agent, and then you can actually calculate the gradient, basically, of the expected reward you get with respect to the parameters in your network. And then you can do gradient ascent to change the parameter in the network in order to maximize the rewards. Now, there are a few subtleties behind it, but that's probably the most effective to implement. There are also much better variants than that. That's still unstable, has a high variance. You need to do more tricks to make it worthwhile. But there are some really good libraries existing. My favorite is Stable Baselines 3, and that is implemented in PyTorch, and it's very well written, very pretty simple to use, and very powerful. There are more powerful libraries, but you pay the capabilities with a much increased complexity. And the field is already complex enough. We don't need that much more other complexity. So I think SB3 is a really good library.
So what are some interesting things that you've seen or thinking about lately in terms of?
Yeah, so thinking a lot about in this kind of end-to-end learning, how to incorporate multiple tasks in an easier way. So the idea is that we can do reinforcement learning with multiple tasks, like in the same way we do supervised learning with multiple tasks. In supervised learning, you collect the dataset with all the data from the different tasks together, and they just sample mini batches from all the tasks together. And that takes longer to train. In reinforcement learning, it's the same. You can just take a lot of parallel environments, and each environment can be a different task. And then you just have your agent interact in parallel in all the possible environment, all possible tasks it needs to solve, and then pull together the experiences and learn a single model that can perform all the tasks. But it's very difficult. One, because reinforcement learning takes a long time to train. So this is kind of scales almost linearly with number of tasks, and it makes much more time consuming. Second is some tasks may be easy, some tasks may be difficult. And usually you need a lot of hyper-parameter optimization, or even like engineering of the reward function, because maybe your agent cheated on the reward function and then you need to change the reward function. Now imagine that you have a lot of tasks, and some of the tasks, the agent learns to do them. The others, it fails. Then you need to change either the reward function, some parameter or something. But then you have to train the whole system again with all the tasks, even the one you already learned. That's kind of stupid. But that's the traditional multitask approach. So there is a better way, and a better way is it is like not entirely novel, but I'm working on it now as well. But I'm not the first one to do, and that's called multitask policy distillation. So policy distillation is similar to knowledge distillation in supervised learning, but with some subtle differences. So when you do knowledge distillation in neural networks, you are usually want to take a trained neural network and create a smaller neural network, so for example, to use in an embedded, in a robot or in an embedded chip, but that does the same behavior. So given the same input, you want the same output. So you basically give the same inputs to the bot network, and you train, you use for example, a KL divergence loss so that the output of the two network is the same, or mean square error, depending on what type of output the network is outputting. So you basically train the network that given the same input, you want them to have the same output. In reinforcement learning, this is used differently. So this is used differently because we don't really care about using smaller models. In reinforcement learning, usually neural networks are pretty small. They're becoming bigger because there are many more benefits of using larger networks. But usually in reinforcement learning, we use small networks because they are faster to run, and again, the training is low. However, what happens in the field, when big companies that can afford it, even when they do the reinforcement learning, it turns out that during training, you train your model like AlphaGo, and you get good performance, but you want to get better performance. So you make some hypotheses, you change the city representation, you change the network architecture, hyperparameter, reward function, whatever, and then you have to train from scratch. But that's really stupid because maybe you spent $20,000 to train that big model once. Then you throw it away and you train again for scratch with that hyperparameter. Even if you have so much money, as DeepMind OpenAI, it's still a really stupid usage, and you also waste a lot of time. So what they found out very early on, at least in the past quite a few years, is that that's stupid indeed. So what they do is, imagine you want to try different network architecture. Okay, you take the previous trained model that was working, not at the best performance, but it was working. Then you do policy distillation, which is basically you train a new neural network with inputs from the environment. So when the agent is interacting with the environment using the trained policy, and then you train the new network to output the same output as the previous network when the same input was given.
Okay, so smaller. It's like an autoencoder.
No. This is like you just take two neural networks with different architecture.
Okay.
One is already trained and you spend $20,000 to train. The other one is blank, initialized at random. But before you start using the new network, you first train the new network. You give the same input to both networks, and you observe the output. Then you create a loss function that penalizes differences between the outputs of the network. And then you train a new network to basically mimic the old one. Yeah. But now you have a network that encodes all data learned already, but you get a bigger network or with different hyperparameter. And then you continue training, with the new network. But now the network is different. And you could not have done this change before, because if you need to change the network architecture, you're adding parameter, but they are initialized at random. So in this case, you actually encode what has been learned in another network. And actually, contrary to knowledge distillation, we usually do the opposite. Instead of going from a bigger network to a smaller one, we go from a smaller to a bigger one, because this way we can train faster on a smaller network and extract something from the environment, and then continue training on a bigger network, which is more time consuming, but we hopefully need to train for fewer time steps because the network has already learned a lot of baseline. So this is one way. Another way is to do multitask policy distillation. So if you do multitask learning, but instead of taking one network and cloning it into another network, you take many networks, one for each different task. And then you do policy distillation by collecting data from all of those, giving different inputs. You see, so you basically do policy distillation at the same time with all these other networks, but they all go to the same unique network. And it is that then you have a network that can do all those tasks. if the distillation is successful. But because you have an individual task for each behavior, if you need to change behavior because you don't like it anymore, you can just retrain the policy distillation step, which is much faster than training from scratch the whole agent. Or if you train the different task and one task is not learning, you can engineer the reward or change the parameter only for that task. And once you're happy that the performance is good, then you have that train your network for that task. And then again, you put them all together in one single network using policy distillation. And that can basically allow you to swap in and out this behavior, and it can be much more useful for practical,
so you train,
in commercial applications also.
You train smaller tasks, and then you bring them together into one big network.
Exactly, yeah. Because this way you have more control on how each task is learned, and you can make sure that each task is solved as you want it. But you can do more advanced things that. So you can use this behavior not as multiple tasks, but as skills. So kind of a skill prior. So this is what OpenAI did. They train an environment in which 3 humans with like I think 72 or 80 degrees of freedom, so like very many type of very very complex movement, and they wanted them to play football against each other. So they first had to learn to control the body, which again with the 70, 80 degrees of freedom is a very challenging task. It can be done with reinforcement learning, but it's still not super easy. And then they need to learn the rules of football, and then they learn to strategy, how to evade an opponent, how to score a goal, how to trick the opponent, the more advanced skill. So this, if you were to train a reinforcement learning agent on this task from scratch, you just put these agents at random, and the reward is +1 or -1 when every time the goal is scored. You see them doing nothing. Actually, there is a video of them training, and you can see that when they start learning, they have nothing. So they just fall to the floor and move at random like they have like an epileptic seizure. If they were doing those movements at random, they will never score even one time the goal. So it will take forever to learn. So OpenAI was very smart. They put together a lot of components, which I think are really good. And it's kind of an indication that now it's still complicated from the engineering, like software engineering side, but it will become easier. And once this tool become easier and more accessible, then I think that this is kind of a paradigm that will be the base of actual commercial application that use reinforcement learning, for example, especially for robotics. So it was as follows. First, they started with creating a low-level motor controller that can control the robot, this many movement that the robot can do, to do all the action it can care, like running, walking, kicking the ball, and these kind of things. And this is trained using motion capture data from actual football players. And they're used to basically create a model of what type of movement are probably good for solving this type of task. Now, there are a lot of other tricks in the process, but this is the main one. So after training this model, we get an autoencoder that takes a latent vector as input and outputs sequences of motor action. This latent vector is much better than motor control, because if you take a motor action at random, like a joint position at random for every joint in the body, most of those combinations will not be combination of movement that a person would ever do, because it just be random movement of all the joints in your body. But if you take a vector at random in this latent space that is inputted to this low-level controller, then you actually output a realistic configuration of the body. So if you output actions at random...
just make the search space smaller.
Yeah, but also every random vector in this latent space is always a correct configuration of the body, while most of the random vectors in motor space are not realistic.
Not legal, they're like illegal.
So yeah, if reinforcement learning learn by exploring at random, if it explores at random in the motor space, it will take forever to find which motor combination are correct.
There are many more illegal states than there are legal.
In this case, it is guaranteed that it will do something at random. It will just walk in a random direction, but it will be walking, not just falling to the ground and having an epileptic seizure.
Right.
So that's a big advantage that speeds up learning a lot. The second trick they found is to train these skill modules. And the skills module are this simple neural network. Each of them learns to do a simple hard-coded task. One is just kicking the ball. Another is kicking a ball towards a specific direction. Another one is running, or following a path. So there is a path like a key point, and the agent is given a reward every time it moves toward that point. Then the point moves, and the agent has to follow. And other one are about crossing opponent. There are a couple of skills. So they have like 3 or 4 of these skills. And these are easy to learn because it's a single task. And the agent has already learned to do this kind of complex locomotion. So if you explore in this high-level motor space instead of the low-level motor space, it's much faster to find correct configuration movement.
So you teach it little individual skills, and then you
Yeah,
put them all together and create
then you
the whole thing.
combine them. But then if you combine them in a multitask setting, that's not what you want to do, because then you have an agent that can do those 4 movements and all 4 actions, but it's still not playing football, right? There are no rules of football. So what you do instead is you train from scratch, the agents to play football using this low-level controller, so you don't have to output this motor command directly, so it is already much faster. But you also have a special loss function that basically is a mix of policy distillation and action reinforcement learning. So the agent is learning by reinforcement learning using +-1 reward when the ball enters a goal. But until you get those rewards, there is an auxiliary loss, and the loss is the distillation loss. So if the agent does not have any reward signal because it did not collect reward, it will learn to reproduce the 4 learned skill that it learned. So it basically, when in doubt, it tries to mimic one of those 4 behavior. And that makes it more likely that you select the right action, kicking the ball and at some point getting a goal, then you get a reward, and that reward will change the behavior. And then if the robot is or the agent is confident about the behavior, then it will start ignoring the skills, these 4 behavior, and will focus on the one actually get the reward. And this is tuned automatically. So the model automatically balances how much weight to give to each of the skill. So you can select which skill is more useful to use, to learn in that part of training. And then the agents learn really, really well and really good strategies. It still takes an insane amount of compute power to do all this process together. It could be done probably in a bit simpler way, a bit less performant, but also simpler and a bit cheaper. But it's still barely within the reach of academia. So I think that computationally we may be able to do it, but to still be at the limit of the cost or resources that are available. But the infrastructure is really difficult to make, so it will take time to actually get to that point.
There's a lot of concern about the access for academics to do these kind of next level AI things, just from a compute perspective.
Yeah. So, sorry, 1 second.
So is it going to be the case that like in the future it's just going to be Microsoft and Google doing all the research for AI stuff?
Sorry again? Yeah, sorry, got distracted.
No. It's like just the cost of doing AI research.
Yeah, but that is going down. So there is a survey, I don't remember the name, I think... it's something with AI for robotics, but there is a survey that is being done for a few years. This is released every year, and they keep track of progress in robotics in the field. And one of the things they track is the cost of the robot platforms, and you can see that they are going down exponentially. So,
I see.
And that I think comes hand in hand with more people accessing the field. The more people are in the field, then the bigger the market, so the cheaper this robot can become, and also there's more incentive to make it cheaper. If it is only companies like OpenAI and DeepMind who have deep pockets, then they can afford to spend a lot of money on these robots, but the other labs, most of the other labs and companies cannot. So that keeps the people out. And because both of these companies are very close in their software, even if they develop this software infrastructure, that is not accessible to other people. And when you have to create it from scratch, it takes a lot of software engineering, and they have big teams of software engineers, doing the actual coding. So that's why I think, being more open source, both in the robot platforms and in the software, is going to be really useful. Now, every paper we're making, we are open sourcing the code, and if the code is useful, for example, I usually also write a Python library that actually makes it even simpler to use the code, because most scientific code for paper is really designed only to reproduce a paper, and is really messy to work with because you have to really modify a lot of the code. But if you can package it as a Python library, then people can just install it and then just use it in a high level, using some example that you can provide. So these are all things that definitely help, but they take time to develop. I just want to stress that, OpenAI, despite the name, is one of the most closed source companies in the world. They really change a lot from the original mission. So
what about Tesla bot? Not going to happen?
Let's not talk about it.
Well, no, let's talk about it. Come on. What do you think?
As a robotic platform is ridiculous. It's much less than the state of the art of human robotics, and it's only a marketing ploy, to attract people to go to work for Tesla in AI. There will never be a Tesla bot. It will never really work. It will only be a prototype, for.
What's wrong with the idea?
No, the idea is good, but robotics is really expensive. Elon Musk in the presentation quoted the price of 20,000 euro, but there's a big asterisk. That price is quoted for, I think, a production run of 1,000,000 of them, and of course, everything can become like cheap, if you build 1,000,000 of them. So yeah, the actual robot is probably in the hundreds of thousands dollars right now.
But like, can it work though?
Huh?
That's the question. Can it work? Like,
I mean,
what's the
there
idea?
there are lots of humanoid robots in the world. Atlas robot is much more advanced, for example.
Right. So like, I'm honestly no idea. Like, what are they claiming that this is gonna do better than the other things that are out there?
Because Elon Musk has a very big ego. But again, I don't think they actually believe that. I think that they keep it as an open possibility, because of course, if they can do it or they feel developed well enough, it is definitely a big market to tackle. But their team working on that is actually also very small, and I actually don't think they are actually serious about it. It is really only a marketing stunt to get people excited, to get people to talk about Tesla and Tesla AI, and to get people who maybe don't care much about self-driving car but want to do AI. They think, oh, it's a cool robot and cool AI for robotics, and they can hire them and then do good science, good engineering and science for them, for their team. But yeah,
I guess that they probably have to solve the self-driving first, right?
not necessarily, but yeah. But also,
Is it a harder problem, do you think, than the robot, or no?
Yeah, but only because it depends on what you want the robot to do. So I think that there are other companies, like there's one, I think it's called Everyday Robots, if I remember correctly. It's a spin-off by Google X. So, and they actually were doing a lot of reinforcement learning for robotics. So I was excited. But then it turns out that they actually kind of doing a lot of mix with this traditional type of robotics that they're not very fond of. Now, there is a problem with that. Most companies in robotics like this that do these human robots, I think they are aiming too high. So we will get there, absolutely 100%, and even not in not that long time. But you want a robot that is from a domestic helper. The number of tasks you want the robot to do in the house are many and very complex for a robot. Like from even just cleaning or making coffee or something. These are really, really difficult to train this robot to do them, because every house is different, so the robot has to be adaptable. The robot has to be able to learn if you want the task to be different, or the coffee machine is going to be different people. So a lot of complexity that you can do with end-to-end learning, that you can fine-tune it with this kind of handcrafted behaviors, and it's a nightmare. And it will never work, with this kind of techniques, it will never work at the level of performance to actually work in daily life. That's even setting aside the cost of the robots and everything. So I think that that is the main problem. So it's not about, it's good to aim high, but I think that if you start, if you want to build a plane, with the Wright brother, imagine if instead of building that simple plane, they tried to build the F-35, from scratch, without even building the first plane. It will go nowhere. So it's good to aim high, but I think you have to be a bit more incremental. And of course, there is the appeal, because if you have a domestic helper robot, that's a massive market, and that's what many robotic companies are aiming for. But I think that they will not be successful. And robotics companies are a massive drain of money. It costs a lot of money, and you don't get returns for 10, 20 years. So, you really have to have very deep pockets to support that.
I mean, it's only the Roomba is the only thing that's really...
Yeah, true. But that's because the task is simple. Exactly so. So what I'm thinking is that is not the right approach. So what I'm interested in AGI and artificial life and actually synthetic life, also for Fermi paradox and a lot of interesting topics. But in general, I think that a very good setting, both for research, especially in artificial life that I'm interested in, but in general for reinforcement learning for robotics, and also as commercial application that is much more realistic, is that of robot pets. Now, for robot pets, you should not imagine a dog just a robot. It should be like a new animal. But there are a couple of good things about that. The first one is that a pet or an animal, they can do a lot of different behaviors, but the behavior they do are usually much simpler than the type of behavior we would like in a domestic helper robot. Because a pet does not need to basically be able to do anything, right? It has to be entertaining, it has to make an emotional connection with you, it can be playful, maybe play fetch, because there are some things that are a bit more complicated. But you don't expect a pet to be able to do a complex task like make you coffee. So, a robot pet does not need to be able to do tasks, okay? That's the big thing, but it has to look very realistic, or it has to be alive, okay? That's the main thing. But that is kind of independent from the type of the behavior. So I think that this puts the bar much lower and much more attainable. Now, what I mean by being alive or looking alive, depending on your interpretation, in my case, I think in that sense it could even be alive, or when you get to a sufficient complexity, but it can be debated. The idea is that if there is a kid that has never seen a giraffe and sees a giraffe for the first time, it will look weird. But they will not see a fucking alien. They will see it's a giraffe. They can tell it's an animal. They can look at moving around. They can see grazing. So they can put they can relate the new animal with existing animals, and they see it moving in a certain way. For example, there is such thing as biological motion. So if you take markers and you put them on an animal or a person, and you only show the video of how these markers move on the screen without showing the animal, and you compare them to randomly moving dots. Even infant chicks or animals or in the humans have a strong preference for the dots that move mimicking the movement of an animal. That's called biological motion. So there are things including biological motion and coherency of behavior, not the robot that keeps bumping in the wall because it does not detect the wall, but more as in being consistent. So if you call a robot dog, like a robot pet, say come here, and if it just keeps staring away, does not even move, you can tell it did not detect you, and you can tell that the robot is broken, right, or something went wrong in the program. So that you will see that that's like a machine, not like alive. But if you call it and it turns to you, a dog that can move the head and look at you like kind of a puzzle, and that does not come to you, you will not think that the robot is broken. You will think that either it does not want to come to you, or it did not understand the command because it's a puppy, and does not understand what you mean by come here. There could be a lot of reason, but you will not be shocked. Most of the time you call a dog, it will not necessarily come to you unless it's your own dog, and you don't think that the dog is broken. So I think that there are simple things like that in this case, if you do this behavior, and I think that the key to make it like this coherent is being end-to-end. But if you get a robot that does that type of behavior, then it does not need to do the task correctly. It can make mistakes, but as long as the person is not aware that the mistake is due to the controller not recognizing the command, and the user think that just the robot does not want to do it or did not understand it, but it is still alive and looking at you and moving, then I think it's fine. Most animals we have don't do what we want to do or what we expect them to do the vast majority of the time, and we don't think they are broken. It can be a bit more dumb, or they can just not want it, or they not understand the command. It can be a lot of reason, but they are not broken. So that's why I said that you don't. It's much easier than a domestic helper because it does not need to work. It has to be alive.
It just has to be alive.
Yeah, it has to be alive and do possibly make an emotional connection with you, recognize you, bond, possibly learn some tricks that would be useful, and have some memory and have a different personality. So different pets have different personalities, and be maybe sometimes funny or entertaining. So there are some things that you might want in a pet, but it does not need to be able to do stuff. That's the key.
Can that be achieved by just standard classical robotic stuff?
No, I don't think so, because in that case, imagine if it is kind of module-based controller or a finite state machine. If one of the rules that control the state or they control one of the perceptual modules, like detecting face, breaks, then you get the robot that stares in blank and does not respond to you because it is not detecting you. And it only takes one time to see that effect to break, you can call it as a delusion or to actually not be alive. Again, it can be debated in philosophy. But either way, you will not see it as an animal anymore because, once you see it breaking, you see, it's very convincing, but I can see, it's just like an if-then rule. But if it is consistent, as I'm telling you, like for example using end-to-end learning, there is no single point of failure, and then the robot will never be staring it blankly or be visibly broken as if an if-then rule, was not met. And that's the most important. So the user should never see that happening. If they see that happening, then they don't. It will not consider.
There have been quite a few attempts at the pet, right?
Yeah, but they only use this existing technology, not this new recent one. And I think this is actually the key.
Nice. Well,
but we'll get there anyway. Yeah. So
do you have? I think you have a meeting to go to.
Yeah, I have 5-10 minutes, but.
Anyway, but this has been great. Because I was speaking to Marianne about how learning happens in the human brain, and it's nice to think about how it could be implemented in a machine. But man, it's such a it's a qualitatively different sort of approach than to other traditional machine learning sort of things.
Yeah. But if you want to learn a behavior, there are no other way. I mean, there are some alternatives like self-supervised learning, imitation learning, inverse reinforcement learning, all these kind of things. But in the end, they are all very connected to reinforcement learning because that is the way to learn behavior. Like even mathematically, there are also parallel with control theory. When you do mathematical control theory, they use different notation. But there are a lot of people have noted that the equations have the same form. So even if you do traditional control reinforcement learning, you call the variables in different way, the function is slightly different, but it's really doing something very similar. So there are probably not many ways to learn a behavior other than that. That's regardless of the parallel with biology. And that's actually how I got into reinforcement learning at the beginning. So I was interested in AGI, and I was excited. I come from a background also with computational neuroscience as a PhD, and I studied the brain, and then I saw the progressive with deep learning. I say, okay, that's actually very useful. That's what I need. But with traditional supervised learning, you don't get to AGI with supervised learning. No, I think it's going to be pretty impossible.
So ChatGPT won't take us to AGI?
I think there are many approaches to AGI. I think that many can do. I think that in a sense, GPT, I don't like ChatGPT. I prefer GPT, the actual model, because I don't think you should be able to chat with the model. I think that's kind of stupid. But some people like to not talk with the computer. But if you use it better, you can just use the prompt in a smarter way. But anyway, so GPT, in a sense, it is a general intelligence because it can do multiple tasks quite well. You select different prompt. It's not learning one task, but it can do many tasks. And that's kind of like a general learner. So that's a general learning system. So in a sense, it is a little AGI, but my definition of AGI is much more liberal than other people. For me, an AGI is something. So there should I follow a nice paper by Ben Goertzel about this, about how to define intelligence. And one way to define it, I think there are two directions. One is how good you are at solving a certain task. The other one is what is the set of tasks that you can do. And if you're able to learn a wide range of tasks, then you're a general intelligence, and you are more intelligent if you can do those tasks to a better performance, like superhuman performance better than human. So in a sense, if you have like a narrow intelligence, it's going to be an intelligence can be arbitrarily smart, but on a single task or very few tasks. And the general intelligence is just intelligence is more or less intelligent, so capable of solving different tasks on a wider range of tasks. And GPT is able to solve and to learn to solve a pretty wide range of tasks. So in a sense, it is an AGI. It is not human-level intelligence. It is not human-like intelligence, but in a sense, it is a simple AGI. But again, when we talk about AGI, we usually mean more complex and more capable systems. So that's the only difference. So I think that a much more capable version of GPT could definitely be an AGI. Not the AGI that I'm interested in. I think it'd be limited for a lot of reasons.
Would it have to have a body? Would it have to have a body to be like for AGI to sort of do a thing?
I don't think so.
Just embodied.
Yeah, I don't think so. But I think there are also different type of AGIs, because again, if you think of my definition of AGI of just having this like wider range of tasks that you can do at superhuman level, for example, then you definitely don't need the body, because again, you can just do all the tasks on the computer. Yeah, hi, we almost finished. Yeah. Yeah. Hi.
Okay.
Yeah.
We're done, bro. Okay, yeah. It's fine. We'll catch up again soon. Thanks again for
thank you for inviting me.
No worries, man. Thanks. Always fun. Next time we'll pick a different topic and talk about it.
Yeah, sure, absolutely.
Yeah, maybe AGI.
That could be, or that or Fermi paradox.
Oh, let's do that. No, let's do that one. I've been wanting to talk about that one. Let's do that for sure. All right.
I'm very passionate about that topic.
Catch you next time, man.
Okay.
Bye.
Then see you next time.
This has been another episode of the One Deeper podcast. Thanks for tuning in. I hope you learned something. Catch you again next time.